Hello, this is James Camp from Lee College in Baytown, Texas, and this is my comments on Chapter 2, Introduction to C++, of Starting Out with C++ by Tony Gaddis. This is for a Introduction to Engineering class, but it'll work in just about any introduction to programming in C++. All right, the parts of a C++ program, the anatomy of a program. You have a lot of things that you can include in a C++ program. You can include comments, preprocessor directives. You can define namespaces and use them. And you can define a function. Okay. The essential piece of any C++ program is a function. Okay. And there's always at least one function called main, which returns an int type, which is a legacy from back when the way you communicated an error code to the computer was returning that code to the computer at the end of your program. So as long as we return 0, the computer knows that everything operated fine. The main function opens with a curly brace and closes with a curly brace. That defines what C++ calls a code block. Okay, and the middle of that, inside that code block, all we have for this program is an output statement, hello there, which is a little odd. Traditionally, our first program is supposed to say hello world, but they've decided to do hello there to be a little bit different. And once we've accomplished our one line of code, we return the value 0 to let the computer know that there were no errors. You can see some special characters found in a lot of C++ programs. The double slash in this previous page we looked at is the beginning of a comment, the beginning of a one-line comment. We'll talk about comments more in a little bit. The pound sign indicates the beginning of preprocessor directives like pound include and pound define. It's not a hashtag, as you might expect from the Twitter era. It's a directive to the preprocessor that operates on the file before the compiler operates on it. There are angle brackets, sometimes called diamond brackets, that operate on the file names that we want to include with pound include. There are parentheses that are used to name a function. They're also used to group together related statements in a or higher priority statements in a mathematical function. They have several different uses in C++ depending on context. And then these curly braces enclose a group of statements into a code block, in this case to constitute a function called main. You saw open close quotation marks in that around the hello there phrase. That tells C++ that you want to take that string of characters as a string literal, as just text. And then you saw some lines ending with a semicolon. All official executable code statements in C++ end with a semicolon. Okay, so let's walk through some of the things we found in that basic program. The cout object is what you use to display output to the console. That's what the C stands for, is console output. And it displays output to a console, which is usually a little terminal window on the computer screen on a modern computer. You use the stream insertion operator, less than, to send output to cout. So it operates pointing as if you're pointing this output into the cout object. So we take the string programming is fun and we're smushing it into the cout object. Can be used to send more than one item to cout at a time. Okay, we can have a string of cout insertions in one line. This takes hello and there and smushes both of them into cout in order, so it'll put out hello first and then there. This would be equivalent to writing cout hello on one line and cout there on another line. Once we have a semicolon, we stop allowing you to add more less thans. We have to say cout again. C++ ignores whether you've hit return and included a semicolon. So cout programming is followed by cout fun will produce programming is fun on a single line. If you want to end the line, you use the end line output manipulator. Okay, that end is a lowercase l, not a number 1. Okay, a lot of people will, a lot of first-time programmers will type end 1 there because it looks a little like a 1, but that's just the way typewriter fonts make the L look. So programming is end line fun will format the text this way. Programming is on one line, start a new line, fun. You don't put quotation marks around end line or it'll actually print out the text ENDL, right? And the last character in inline, as I mentioned, is a lowercase l, not a number 1. Okay. Another way to insert a new line is to use what's called an escape sequence. In C++, there are a number of predefined things that start with a backslash. Backslash in is probably the most commonly used one. That's a new line. You can also do backslash and a quote, and that escapes that next quote line. So if you want to actually have quotes in your text, you have to do that. And you can even have 2 slashes in a row so that you can get a backslash character to print out. Otherwise, it treats the backslash as an escape sequence. So programming is backslash new line fun will produce the same effect as sticking an end line operator at the end. Okay, let's move on. The pound include directive. This is a pre-processor directive. It's not part of the C++ language. Well, it technically is, but it's not part of the language that the compiler recognizes. It's pre-processed before the compiler gets to the program. And the pound include lines, therefore, are never seen by the compiler. Whenever it hits pound include, say, IO stream in this case, it just replaces that line with the entire header of the IO stream library, so that all of those things are now part of your program. That whole library is now part of your program. Do not place a semicolon at the end of the pound include line. It really won't hurt your program if you do, but there's no reason to. It just C++, the compiler would see this extra semicolon floating there and not know what to do with it. Some things that we haven't used yet in our simple program are variables. Okay, variables represent a storage location in memory. So if you remember from the previous presentation, we talked about memory being made up of a series of memory locations, which you can think of as little storage boxes for computer values. And normally they have numbers like 0, 1, 2, 3, and etc. But if we want to refer to one of them in our program, always going back to memory location 002 is a little bit difficult, and it's inflexible as well. So we can take the identifier item and stick it on this memory box. Okay, and this tells it not only that item belongs to that memory box, but that the value held there is going to be an int type, an integer. In contrast to a variable, a literal is a value that's just written straight into a program's code. For example, hello there is a string literal. 12 is just an integer literal. Okay, an integer, if you're not familiar with that term, is like a whole number, a number that does not have a fractional part, does not have a decimal point in it. Okay, this is an example of using a integer literal in a program. We assign it to the value apples, and then when we call variable apples in this output statement, it already has the value 20 from that integer literal. These are examples of string literals. We're actually not assigning those to a variable, we're just sticking them straight into cout. That's really the only literals that you should ever put in a cout statement are string literals. It doesn't make sense to always stick text into a variable every time you want to output text, but we tend to frown on just dropping numbers into an output statement because apples might change from one time that you run a program to another, and trying to figure out what that 20 meant is difficult. We try to, when it comes to using number literals, we try to avoid the use of what programmers call magic numbers, where 20 just drops into the code with no explanation. It's much better to do this where you say apples equals 20, and I know, oh, okay, 20 is the number of apples we had on that day. And then if I want to edit the program to sell 32 apples instead, I know exactly which number I need to change. It's the number of apples. Okay. If you're going to use variables, you need to give them identifiers, meaningful names. Okay. You cannot use any of these C++ keywords as an identifier. If you try to use auto as an identifier, you will get an error. Other than that, identifiers can have almost any name you want to give them, with a couple of exceptions. The first character has to be an alphabetic character, A, B, C, D, E, F, G, or an underscore. By convention, underscores are not usually used as the beginning of variable names, except in some very special cases that we're not going to discuss here. After the first character, you may use alphabetic characters, numbers, or underscores. People often use underscores in replacement for spaces. So if I wanted last name, I could do last underscore name. They're also sometimes used as a way to indicate subscripts. So if I'm trying to indicate velocity in the x direction, I might type that as v underscore x. Here are some valid identifiers. Total sales, yeah, that's fine. We used something called camel case here, where we begin each new word with an uppercase letter, and it looks like the hump on a camel. Here we're using what programmers call snake case, where you stick an underscore between words, and it looks like a snake slithering across the screen. You cannot break words with a period. That's because periods in the middle of identifier names have special meanings in data structures and objects. You cannot begin with a digit, and you cannot anywhere have special characters like a $sign in your variable names. Okay, let's quickly tour the variable types in C++. Integers can hold whole numbers such as 12, 7, -99. A short int is 2 bytes, and it goes negative, that should be a 1, 32, 768 to, no, should be negative 32, 768, that 2 shouldn't be there, and that 1 shouldn't be there. Should be negative 32, 768 to 32, 767. If you do it unsigned without a negative, you get twice as much range. On the positive side, you get 65, 535. Ints are what we usually use for integer numbers. They obviously, you see, can hold a much longer, again, we got that -2 and +1 here that shouldn't be there. But they can hold up to, let's see, 1,000, million, billion, up to 2 billion. So that's a pretty wide range of numbers. That's about as much as we need for everyday integer calculations. If you need twice that range and can give up the negative numbers, you can use an unsigned int. And again, we have this -2 and +1 that shouldn't be there. Long ints in practice are still 4 bytes. If you want more room, you need a long int, which is 8 bytes, which goes up to 9 million, well, really big. I don't remember how many spaces there are after the decimal point, or how many sets of these there are. And my little picture here is blocking the screen. Let's see. There we go. Okay, so we've got 1,000, million, billion, trillion, quadrillion, 9 quintillion values. That's pretty good. In defining a variable, some syntax here. Int is the type, followed by length. That's what you want to call it. You can define more than one variable on the same line, as long as they are the same type, by putting a comma in between them. Length, comma, width. But as soon as you put a semicolon, you're done defining that set of variables. You need to start again with a variable type. This program has 3 integer variables: checking, miles, and diameter. Each have different integers that are assigned to them. We define them up here, and then we assign variables to them down here. You don't have to do that. You can initialize a variable in the same okay. You can initialize a variable on the same line that you use it, that you define it, if you want. To assign values to ints, we use integer literals. An integer literal, any kind of string of numbers without a decimal point, is assumed to be an integer, an int, by default. If you put an L at the end of it, it converts it to a long integer. 2 L's converts it to a long. Okay. If you prefix it with a 0, the compiler is going to assume that you meant to put that in base 8. So this is not actually 75. This is 7 times 8 plus 5. Okay. If you begin with the prefix 0x, the compiler is going to assume that you meant to put this in base 16. So that's 7 times 16, 7 times 256 plus 5 times 16 plus a is actually the numeric value 10. Okay, since base 16 can hold numbers 10, 11, 12, 13, 14, and 15, we represent those with the letters A, B, C, D, E, F. And why do we use base 8 and base 16? Why are they special? Well, again, computers store numbers in powers of 2, and base 8 and base 16 are useful for storing memory addresses if we're using an 8-bit or a 16-bit memory addressing system. Another data type in C++, a fundamental data type, is a character. A character represents any value that you can type on the keyboard, essentially. So the uppercase C is stored as 1 character. Okay. You can also store single quote 1. Okay. And you would not be storing the value 1, you'd be storing the character that represents the number 1. Okay. So, and these are stored, the uppercase letter C has a memory value of 67. So it's actually the number 67 that's stored in memory, not the letter C. But whenever you go to use a character, C++ generally understands that you mean the letter whose number is 67, and that's C. There are a couple of different ways of encoding letters that's worth mentioning here. C++ is still tied to the old numbering scheme called ASCII, American Standard Communication Information Interchange, American Standard Code for Information Interchange, which stores all of the English language letters, numbers, and symbols, which you'd find on a normal English language keyboard, or American English keyboard, I could say, in the values from 0 to 127. Beyond 127, there are 128 more values, up to 255, that different extended ASCII codes use for different things. Over time, they wanted to standardize them, and they've come up with several different versions of international ASCII that had different European character codes, but nothing worked for all languages. So eventually, they scrapped ASCII completely and came up with a new standard called Unicode. Newer languages like Java and C# use Unicode to represent all of their characters, but C++ is still tied to this 256 character or 256 value character system. So you can't use, for example, the Greek letter pi in your code. You couldn't say character pi equals pi, even if you had that key on your keyboard. I should use single quotes, not double quotes. Because C++ doesn't know how to store this. There is an extended C++ variant, a 16-bit character that can store all of these Unicode characters, but regular C++ doesn't know how to do that. Character literals must be enclosed in single quote marks to distinguish them from strings, which are double quote marks. So what's a string? A string is a series of characters followed by what's called a null terminator, the character known as character 0 or escape code \0. And this harkens back to the days of C, which did not have string objects, and so it would create an array of characters, and if you wanted to print that out, it would start here and go, and there's an H, there's an E, there's an L, there's an L, there's an O. There's a null terminator. Stop here, okay? And it would print out HELLO and then stop. C++ has a better way of handling strings called the string class. String class lives in a special library called string, so you have to #include string in order to use it. You can define string variables in programs by just, once you've included string, saying string first name, last name, for example. Technically, you should put std : string, because string lives in the standard library namespace. But if you put that using namespace standard that we've been putting at the beginning of all of our programs, you don't need to worry about this standard : bit. So assuming you've used namespace standard, you can just type string first name and you've defined a variable called first name. String values can receive values in the same way that int values can. You just put the string equals and then a string literal. So if first name was assigned George and last name was assigned Washington, we can also use the cout operator to stick the stream insertion operator to stick first name into cout, and then a string literal space, and then last name. Okay. Note that we put that string literal with the space in there. A lot of first-time programmers forget that there are spaces in English, and they would just put first name, less than, last name, and you'd get George Washington with no spaces in it. It's important when you make output statements that you remember where spaces and punctuation, commas, those sorts of things need to be. Here's an example of using a string giving movie title Wheels of Fury. I've never heard of that movie, but apparently it's this programmer's favorite movie. Okay. Finally, the most complex data type in this is the floating point. I say most complex because it is not always what it seems. Floating point numbers are stored in a form similar to scientific notation, but it's scientific notation in binary. Okay, so you would have 1.0100101, essentially then times 2 to the 10110, and you have to interpret all of that as binary. What that means is that numbers that are even powers of 2 are represented by floating points very, very well. So 0.25, okay, is 2 to the -2 power, 1/4. Okay, that can be stored exactly as a float or a double or a long double or anything. 0.1, what we regard in the decimal system as a really simple number to represent, does not convert into binary evenly. It becomes an infinitely repeating sequence, just like 1/3 becomes an infinitely repeating sequence in the decimal notation. So 0.1, when stored as a float, rounds off very quickly and is not exactly 0.1. When it's stored as a double, you hold twice as much information in that number, and so you get a much better approximation of 0.1. Note that all floating numbers are signed. There's always a negative or a positive as the first digit, and so you don't get that thing with integers where you can get twice the range if you keep everything positive. Single precision float is 4 bytes, and stores numbers between 3.4 times 10 to the -38, 3.4 times 10 to the +38. What you don't see here is that there's only about 6 or 7 significant figures in this 4 bytes. Okay, so you may be able to get the range you need to hold, say, pi, but you don't get the number of digits that you need. Double precision not only gets you up to 10 to the -308 or 10 to the 308, it also gets you twice as many significant figures. It gets you up to like 15 or 16 significant figures, and so that's a much better storage format, especially for those of you who are engineers who want to do any kind of technically precise calculations. But even so, you will get rounding errors even with a double precision number if you're using enough digits. How do you specify a floating point? Floating point literals can be given in fixed point notation, where you just write them out as you would a decimal point on paper, or they can be used with E notation, where the E represents times 10 to the power. Okay, so 3.14159E1 means times 10 to the 1. Okay, 6.25e negative 5 means times 10 to the negative 5. So that's going to be boom, 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 boom. 1, 2, 3, 4, 5. So that's going to have 1, 2, 3, 4 zeros before the 625 if we wrote it out this way. So that's exactly the same number. Aha. Okay. When you write a decimal fixed point or an E notation number, it's going to be treated as a double by the compiler by default. If for some reason you want to lose precision, you can force it to be a floating point, a float, a single precision. Or if you want to try to access a long double, you can use a capital L after it. Okay. This program uses a couple of floating point numbers indicating the sun's distance and mass. Okay. Moving from a very complicated data type to a very simple one, the bool data type has exactly two values, 1 or 0. 1 means true, 0 means false. And so bool is used to store logic values. You can either have a true value or a false value, and that's it. May seem like that's absolutely silly and not going to do you any good in a real program. Why would you only want true or false values? But actually it comes in handy really often. If we want to do a certain process until we're done, okay, and done is measured by a couple of different criteria, rather than taking a statement that says while and we list out all these criteria, it's a lot easier, instead of saying while and then listing out all these criteria, it's a lot easier to say while not done. And then later in your program, you say done equals this criteria and that criteria and that criteria. And if you just define a bool variable called done, that works out. By the way, bool is short for Boolean, and it harkens back to a English mathematician named George Boole, who created a whole system of calculations, a whole algebra around logical true-false values, and it's now today called Boolean algebra. Okay, I'm not sure why you would want to, but it's in the presentation here, so I'm going to mention it. If you want to know the size of the number of bytes that a particular variable in your program is taking up, you can use the size of value, and it will tell you that the double is taking up 8 bytes and that the amount, which is a double, is taking up 8 bytes. Okay, as I mentioned earlier, you can assign a value to a variable. This equals operator works unidirectionally. Okay, it works from right to left only. You cannot say 12 equals item. You could say that in a math. You could do that in math, right? But you can't do it in programming. You can also initialize a variable, set it to an initial value by putting an equal sign and a literal in the same line as your variable declaration. In fact, it doesn't even have to be a literal. You could use another variable here. You could say int length equals height times 2. Okay, if you want length to always be twice height or something like that. You can initialize variables in a comma separated list like we've used to define multiple variables before, and you don't have to initialize all of them. In this case, they left area open. We could type area equals length times width right there and have it. That would be valid C++. Okay. This shows you a couple of initializations. C++ also gives you, starting in the 2011 version of C++, which almost all compilers should support now that it's 2020, a new keyword called auto, which sets the type of the variable to match the type of the initializer. Okay, so if I initialize amount to 100, the compiler is going to see 100, the simplest variable type that can store this, or the most automatic variable type that can store this, is an int. So I'm going to set auto to int. I'm going to set amount to type int. 12.0 defaults to a double, so I'm going to set interest rate to a double. D with single quotes defaults to a character, so I'm going to set stock code auto to a character. This time the person has put an L because they want to make sure it gets converted to a long number, so customer num will be set as type long. Okay. One interesting concept in C++ is scope. When you define a variable, that variable is said to be in scope within a part of a program in which the variable is legitimate and can be accessed. Usually that's the set of curly braces that most closely surrounds it. A variable cannot be used before it is defined. So you can't say cn x and then int x. Okay, C++ does not read backwards. And the variable can't be used after it has gone out of scope. So if I define the scope within a set of curly brackets that are part of an if statement, for example, once I leave those curly braces, x can't be used anymore. Variables defined outside of any curly braces, this is actually possible in C++, it's not possible in some languages. Variables defined outside of any curly braces are said to have global scope. That means any part of your code can access them. In practice, that's considered somewhat dangerous. We try to define variables more locally. So in engineering, global variables are usually used only for defining a constant. For example, if we want to define the acceleration due to gravity as g equals negative 9.81, you can define that once before you've written any other code as double g equals negative 9.81, and then that's globally available. And that makes sense because you don't need to redefine g every time you write a new set of curly braces. Okay, this is an example of a value being out of scope because it hasn't been defined before it was used. Okay, we have to take this int value equals 100 and move it up here before cout can use that value. Okay, arithmetic operators. A unary operator is one that just changes the sign of the, or changes some property of the value that follows it, usually a sign. Binary operators take two inputs, one before the operator, one after the operator. Almost all mathematical operations are binary. A ternary operator, this is pretty unusual. C++ has a built-in if-then statement that's ternary. It says if expression 1, then do expression 2, otherwise do expression 3. Binary addition and subtraction work exactly the way you expect. Multiplication works exactly the way you expect. Division and modulus we need to talk a little bit more about. Okay, if you divide two integers, you're going to get an integer. Okay, even if you're using an operator like the cout insertion operator that would take a double. Okay, there's no reason we have to round this, but 13 divided by 5 is not going to be 2.3 or 2.6 or whatever it should be, because 13 is an int type and 5 is an int type. And C++ assumes that if you provide two ints, you want to get an int out, so you'll get 2. 91 divided by 7, same thing, you'll get 13. Now that actually is an even division, so that's maybe what you want. If either operand is a floating point, then C++ will do floating point division. So 13 divided by 5.0 gives you 2.6, which is what you kind of expect. 91.0 divided by 7, even though this is an even division, gives you 13.0 as an output to show that it's a floating point number. What this means in practical use is that quite often we'll say something like int diameter equals 23. Okay, my circle has a diameter of 23. And then later in the program, I'll say radius equals diam over 2. What am I going to get there? I'm expecting this to just take 23, divide it by 2, and get 11.5, but I won't. I'll just get 11 because diam is an int and 2 is an int, so we're going to do integer division. Okay, so always remember to put this as a 2.0 to make sure that you force this into floating point division. Okay, the modulus operator, the percent operator, chosen because it looks like a divided by, it does division, but it gives you the remainder, not the dividend. So 13 remainder 5 will divide by 5, and the remainder 13 divided by 5 is 2 remainder 3. So this will display 3. This is, again, may seem like kind of a strange thing to put in, but it's odd how many times you want to do something every 5 computations, for example. So if I'm counting up numbers and I just want to output every 5th computation, then I can say if times I've done this %5 equals 0, then cout output. And that'll tell me that every 5 computations I'll get a response, and that saves me from having every single response written to the computer screen. Percent requires integers for both operands. 13% 5.0 would give you an error because you're trying to take the remainder after dividing by something that is not a integer. In the math library, the C math library, there is a modulus function that will work with doubles if you absolutely need that for some reason. Okay. Comments, last but not least, comments are used to document parts of the program. Okay. Oftentimes the difference between a good programmer and a mediocre programmer is that the good programmer puts plenty of comments in their code so that somebody else can come back later and see what they meant to do, so that they, when they come back and try to debug the program later, can see exactly what they had intended to be doing there. Very helpful for code maintenance. If you write a program here and then you come back a day, a month, a year later, and you're trying to think, what on earth was I thinking when I wrote that function there? Having plenty of comments is essential to that. Now, I am guilty myself of, when I write programs for my own use, not commenting them enough. So it's a hard habit to get into. And I want y'all to get in the practice of using comments to begin with. Now, this person maybe over-commented a little bit, but that's better than not commenting enough. Some ways that comments can be used, int length equals 12. That's what we call self-documenting code. Okay, we already configure from just the name of the variable what length is supposed to be, but there's nothing in that that tells me what units I'm in. Is it length in inches, feet, centimeters, kilometers, miles? So we have a comment here that explains that that length is in inches. Okay, I really do expect that when you write engineering programs in this class, you will always remember to use comments to indicate what your units are, because engineers operate in this weird world where sometimes we use SI units and sometimes we use what some people call imperial units, what I was taught is called American engineering units, miles and feet and pounds of force and things like that. So you can write the same program and have two different sets of integer literals, depending on whether you're working in inches or feet or meters or whatever. And area is going to be the calculated area. And this is where I think they've maybe over-commented a little bit. You can look down one line and see that they're calculating the area here. But it doesn't hurt, okay? It doesn't hurt to put that extra comment in there, and it makes sure that any idiot who comes in and tries to check this code later knows exactly what they were trying to do with this bit of code. C++ favors the single line comment that starts with a / and then continues on to the end of the line. Multi-line comments, however, are also possible, and you do this by starting with a /*, then putting as many lines of comment as you want, and then ending with a */. You can also do that on the same line, /* comment */, but it's easier for a single line comment to just put // at the beginning and not have to put anything at the end. Okay, named constants. This comes up in engineering a lot. We want to have certain constants that define the problem, the diameter of the rocket or the mass of the projectile or the spring constant of the spring in our shock absorber or whatever it is that we're modeling. We don't want that to change throughout the program. We want it to be set at the beginning and stay that way. Well, C++ gives us a keyword called const that represents a constant value. So all you have to do is take a normal initialized variable. You have to initialize a constant variable. You can't leave it off. You take a normal initialized variable statement, double tax rate equals 0.0675, and then add the const operator at the beginning, and now that will be a constant value that never changes throughout the program. Note that they used capital letters for this for historical reasons that I'll actually explain on the next slide. Constants in programming are often given with all uppercase letters, and that helps you determine when you're reading the program that that really was meant to be an unchanging value and not they didn't make it constant by mistake or something. Or later on in the code, if you didn't read the header where the variable was initialized, the idea that tax rate is in all caps means, oh yeah, that's a constant. Where this comes from is there's an older way to define constants that's compatible with the C language. Const is a C++ keyword. And that's to use the preprocessor to replace every instance of a given text string with a number. And we use the #define keyword. So if I have 12 students in my class, I can #define num students as 12. And then everywhere that I use the words num students with a underscore, the preprocessor will replace that with a 12. Note that there's no equals sign. We're not defining a variable here. We're just defining that every time the preprocessor sees num students, it's going to replace that text with 12. And everywhere it sees pi, it's going to replace that text with 3.14159265. There's no typing to this. As long as this is a valid literal somewhere in the program, you can use it. Also note that like pound include, you don't end the line with a semicolon. And preprocessor macros, as they're called, were always named in uppercase letters, which is, I think, where this habit of naming constants with uppercase letters came from. That was just to show yourself when you're writing this later in the program that that's what that is, that it's a constant value. The downside to using preprocessor macros as opposed to const variables is that the preprocessor will go through and replace every example of num students with 12, every example of pi with 3.14159265. So when you're looking in the debugger later, you're just going to see the magic numbers show up. You're not going to see that they belong to constant names. So if I'm looking through a piece of code in my debugger later and I see average equals total divided by 12, I'm not going to know where that 12 came from. If I define it as a const variable, then I'll say, then when I go through the debugger later, I'll see average equals total divided by num students, and I'll say, okay, I'm taking the class average. This shows a couple of named constants, pi and diameter, and then circumference equals pi times diameter. Works just exactly as you expect it to. Okay. The last note that they give in this presentation is the idea of programming style, which is sort of the visual organization of the source code, how you put spaces and tabs and blank lines in. This does not affect the actual syntax of the program. In fact, as long as you put semicolons in the right places, you could put your entire C++ code as a single line running across the page, and the C++ compiler wouldn't care. It ignores white space completely. But it does affect the readability of your source code. You've noticed that I've put a lot of spaces, and I've even gone through and color-coded some of the things in this. A lot of your IDEs will do that for you. They will put spaces and tabs and color coding in to make it easier to read your source code. Programming style also applies to whether you're going to try to put everything in one function or separate things into several functions or other such things, and whether you're going to use everything as global variables or put them where they belong as local variables. And those are things that we'll address kind of as we get through the class a little bit more. Okay, so that concludes our introduction to C++. You now know enough to be a little bit dangerous in how to write some basic C++ programs that can do some simple calculations, input and output strings and numbers and such. We'll get into even more in the coming weeks, so stay tuned.